All right, today we're starting a new unit. In fact, it's an entirely new type of function. We've been focusing all of our time on linear, and here we are transitioning into what we call quadratic functions. All right, quadratic functions have the U-shaped graph that is called a parabola. You should recognize some of these terms that we're going over today because you've already made the vocab and the flashcards for them. So now we're just putting a picture to what you should already know. So a parabola is that U-shaped graph of a quadratic function. So what is a quadratic function? Okay, so it's this U shape right here. Sometimes it looks this way. This is actually reflected. Most of the time it goes up like this. The quadratic parent function is y equals x squared. You'll notice if you compare it to the linear parent function, y equals x, that it's very similar, except we're adding this squared to it. Now, if you don't know what squared does, all it means is multiply it by itself. So if I was to try to see what the parent function looks like, I would take this -3 and square it, which is the same thing as -3 times -3. Well, -3 times -3 is a +9. Then we take -2 and square it. So -2 times -2 is a +4. -1 and square it. -1 times -1 is a +1. 0 times 0 is 0. 1 squared is 1. 2 squared, 2 times 2, is 4. 3 squared, 3 times 3, is 9. So if I plot these points, we've got the point -3, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. We've got -2, 1, 2, 1, 2, 3, 4. -1, +1, 0, 0, 1, 1, 2, 1, 2, 3, 4, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. And you can see now what a quadratic normally looks like. It's this U-shaped graph. And if you notice, it kind of follows this pattern. There's it in the middle. Those are at the same height. Those are at the same height. Those are at the same height. So let's identify all of our vocabulary based off of a quadratic. So this is the parent function, and here we're going to look at a transformed graph. Okay, so it's a little bit different, but just so you can understand that it's not always going to be 0, 0 for the vertex. All right, so y-intercept. This is one of those words you should already know, where it crosses the y-axis. So right here, this is your y-intercept. Which in linear, all we did was look at the table and see what matches up with that x value of 0. So this is your y-intercept. Okay, then we have symmetric points. Symmetric, okay, means the same on both sides. So I'm looking for where they're the same on both sides. I like to look at it from the table. If you look at these, do you see any numbers that are the same? Look at this. This 8 matches this 8. This 3 matches this 3. This 0 matches this 0. These points, -5, 8, and 1, 8, these are what we call symmetric pairs or points. You can recognize them on the graph because they have the same y value. So for example, this y-intercept has a symmetric point right here. This 0 right here has a symmetric point right there. And this 1, 8, this point had a symmetric point right here. Now notice, yes, these technically do have symmetric points, and these have symmetric points, but I can't see because they're not pretty numbers. They fall somewhere in the middle. For example, this is 0, 5. This is like 0.2 something. I don't even know. So I'm not going to mark those symmetric points. So these right here are those symmetric points. All right, the vertex. The vertex is what's in the middle of the rainbow, right here. This is your vertex. We had all of our symmetric points, and in the middle, is our vertex. So right here in the very middle is our vertex. The axis of symmetry. You've probably heard of axis when you're talking about the x and the y axis, right? Maybe in your geography classes, how you've got the different axis, like the axis that the Earth tilts on, or all those types of things. An axis is just an imaginary line. So it's an imaginary line that makes this symmetrical. So it's what cuts it in half. It is always going to go through the vertex. So the axis of symmetry is that x value of the vertex. For this one, it's x equals -2. Okay, so we've got x equals a number. Anyone recognize that? That's based off of Vux. It's a vertical line. It would have undefined slope, and it's x equals a number. X equals -2 is that axis of symmetry. And from a table, you just look at the vertex and you take the x value of the vertex. X-intercepts. We know what those are. In fact, they're the same thing as one of these other words, the 0. X-intercepts are where it's crossing that x-axis. So to recognize those from the table, you look for your zeros on the y. So here and here, these are your x-intercepts or zeros. So finally, we have the maximum or the minimum. So each parabola is going to have either a maximum or a minimum. So looking at this one, this has a minimum point, the lowest point possible, and it's the vertex. So this is a minimum. So the vertex is the entire point, whereas the minimum is just the y value. So what is the y value of this point? It's at -1. And you get this from the y value of the vertex. So the vertex is super important. The x part gives you the axis of symmetry. The y part gives you the max or the min. All right, so now that we know the different parts of a quadratic, we're going to practice being able to recognize a quadratic. So how do we know that it's a quadratic to begin with? So to determine if the graph is quadratic, it needs to be a U-shaped parabola. Okay? So for this one right here, is that a U? Yes. So this is quadratic. Whereas this one is not a U. In fact, this is a straight line, which we call linear. This one, it's not just a U and it's not a line. This is neither. So we've seen from a graph what it looks like when it's quadratic, recalled what it is when it's linear, and then if it's neither of those, we just circle neither. To determine if an equation is quadratic, it needs to be based off of y equals x squared, that parent function, meaning has a max exponent of 2. So a largest exponent of 2. So looking at this one, it's got that x squared, but look at this x cubed. That's got something else. So this is neither. Looking at this equation, the largest exponent I see right here is that squared, so it is quadratic. This one, it doesn't have a squared. It doesn't have any exponents at all. This is based off of y equals mx plus b. This is linear. So we've talked about from a graph, you need that u. From an equation, you need the exponent of 2. So from a table, you need to have a constant second rate of change. Remember, for linear, the whole thing is that it has to have a constant rate of change. Y'all have heard that before. So all we're adding is this second rate of change. Now, what the heck does that mean? Well, let's look at a table and try to decide, okay? So let's look at this one, okay? So to get from -3 to 0, you're going up 3. Now first notice, all of these x values are going by 1, okay? So to get from -3 to 0, you're up 3. 0 to 5, add 5. 5 to 12, add 7. 12 to 21, add 9. Okay, so that does not have a constant rate of change, so it's not linear, okay? But let's look at what we call the second rate of change. To get from 3 to 5, you add 2. To get from 5 to 7, you add 2. To get from 7 to 9, you add 2. This is your constant second change. So this is quadratic. So let's go back and look at these other ones and see if those are quadratic, linear, or neither. So looking at this first one, notice the x's all go by 1. 6 to 5 is -1. 5 to 4 is -1. 4 to 3 is -1. 3 to 2 is -1. That has a constant rate of change, the first one, so it's linear. Okay, let's look at the second one. 0 to 4, adding 4. 4 to 20, adding 16. 20 to 54, that's adding 34. 54 to 112, that's adding 58. So now let's look at that second change. We know it's not linear because those are not the same. 4 to 16, that's adding 12. 16 to 34, that's adding 18. We can already see right there those are not the same, so it's not quadratic. This is going to be a neither. What about these other two tables? You got to be careful when you go from negatives like here to see if it's getting larger or it's getting smaller. So all the x's are going by 1. 16 to 2, you're subtracting 14. 2 to -2, you're subtracting 4. -2 to a +4, you're adding 6. 4 to 20, you're adding 16. 20 to 46, you're adding 26. So let's see now. It's definitely not linear because that's not a constant first rate of change. To get from a -14 to a -4, this is adding 10. -4 to a +6, again, that's adding 10. 6 to 16, adding 10. 16 to 26, adding 10. This has a constant second change, so it is quadratic. Let's look at one final example before you get started on your practice homework. 2 to 0, you're subtracting 2. 0 to 0, that's no change at all. Those are the same. 0 to 2, adding 2. 2 to 6, adding 4. 6 to 12, adding 6. 20 to 20, adding 8. So those are not the same. It's not linear. So let's look at that second change. -2 to 0, that's adding 2. 0 to 2, adding 2. 2 to 4, adding 2. 4 to 6, adding 2. 6 to 8, adding 2. That has a constant second change, so it is quadratic. So now that you have notes to base off of how to recognize quadratics, you either look for the parabola, look for the max exponent of 2, or you look for the second change. And once you have quadratic, recognizing all those key vocab words. You've got the vertex, which is that max or the min. You've got symmetric points, which have the same y value. You've got the axis of symmetry, which cuts it in half. You've got the y-intercept, where it crosses the y. You've got your zeros or your x-intercepts right there. So now that you have all those, you're going to practice completing the homework. Look back at your notes if you get stuck or have any questions.